Okay, so I want to quickly go over what I want you to do with the Excel file. So this is for the calculation of an equilibrium constant lab, and if you go to the Moodle website, you will find your data, and your data is just these two columns here. If you'll remember, we did um, eight different solutions. We had a set of standard solutions that was these first five. There was a blank, and then there were five solutions, and then we had a set of um, experimental solutions. So if you'll remember how this worked, we had a reaction, and the reaction was the reaction of iron 3 and thiocyanate to form the iron thiocyanate ion. And there was an equilibrium associated with these two things reacting with each other to form this ion. And we're trying to measure that equilibrium constant. So what we need are concentrations, equilibrium concentrations for each of these things. And so what we're going to actually measure is the concentration of this ion, this complex ion, the iron thiocyanate ion. And it absorbs in the visible range. And so what we did was we made some solutions of known concentration. Now let's see how we did that. Here is the actual volumes of the solutions. This was in your write-up. If you look on the write-up on the website, you'll see this. For each one of these, you use 10 milliliters of 0.2 molar iron 3, and then 1, 2, 3, and 4 milliliters of 0.001 molar thiocyanate. This should be molar, so we can, well, we'll just leave it like that. Okay, so basically what is essentially happening here is because we're using a really high concentration of the iron, 10 mils of 0.2 molar in each of these solutions, and a relatively low concentration of the thiocyanate, 0.001 molar, and 1, 2, 3, and 4 milliliters. These are all milliliter units, by the way. That means that there's a large amount of thiocyanate and a large amount of iron 3 and a very small amount of thiocyanate. And we start with no complex ion, no iron thiocyanate. So according to Le Chatelier's principle, what we've really done is we've increased dramatically the concentration of the iron 3. And what do we know when we have an equilibrium reaction? If you increase one of the reactants, it shifts towards the products. And the reactant here, iron 3, is so large in concentration relative to the thiocyanate that we assume that even if it's a small equilibrium constant, it effectively forces the reaction all the way to the end. This is a trick we can use to get away with causing a reaction to happen even when it has a small equilibrium constant. By increasing the concentration of one of the reactants a significant amount, it will push the reaction in the other direction even for a small equilibrium constant. So that's what we assume. And basically what we're assuming then is that whatever our starting concentration here is of the thiocyanate ion, that all of this gets converted into the iron thiocyanate complex ion. And again, because of this Le Chatelier's principle type idea. So when we take the absorbance value and the UV vis of this particular solution, we assume that the entire absorbance is from this iron thiocyanate ion. So what we're effectively doing is producing a solution of this compound, iron thiocyanate, this ion, this complex ion, iron thiocyanate. And that's what we're measuring. Okay, and so what we need to do is figure out what the concentration of this is, and the way that we do that is by dilution. If we start with a 0.001 molar solution here, there was the new solution volume was 10. We started with 1 milliliter of that, and so uh, what we can effectively do is calculate what the concentration is. Now, the way that we do that is there was, I don't have it written on here, but if you look in your handout, there was an additional 10 milliliters, roughly 10 milliliters of a nitrate solution that we also added, and the effect was that every single one of these solutions was a total volume of 25 milliliters. So if we start with 1 milliliter and we dilute it to 25 milliliters, and this was our initial concentration of thiocyanate, and we assume all of this gets converted into the iron thiocyanate complex ion. Then you use M1V1 equals M2V2, and that gives you this number here. So the 0.00004 that I get, if you'll notice when I click on it, you can see that what it does, if you go up here to the formula bar, it takes the value in this F2, which is the initial concentration of SCN, multiplies it by the initial volume, which was 1 milliliter, and divides it by the new volume, which was 25 milliliters. So this, when you hit enter, this is the concentration of the of the thiocyanate, iron thiocyanate complex ion. Over here, this was the measured absorbance, but we had a blank, and so we needed to actually subtract the blank from the measured absorbance. So this is the adjusted absorbance. If you look at the formula bar again, what I have it set here is that we take this number and we subtract this number. And that gives me the 0.072. Now I do the same thing for the one below that. I take this number and subtract the blank. For this one, I took this number and subtracted the blank. For this one, I took this number and subtracted the blank. So these are my values minus the blank. The blank here is just a background. It's what would be absorbed if there were no thiocyanate. So if this is the absorption when there is no thiocyanate complex ion, we have to subtract that out because that's just kind of the standard absorption of that solution, and it has to be removed. So we remove it. These are the absorptions removing the background. Okay, so what we have then, I've just copied the data to this little block here. So now these are my absorbance values. These are my corrected absorbance values. And these are my concentrations. Now I have doubled this up from where I was playing around with it, and not a big deal, but this is the basic idea of the numbers that you're looking at. Okay. Now, what we're going to do then is make a chart. So here's our chart, and this chart is going to be your calibration curve. Okay, and if we'll look at it, I'll zoom out just a little bit here so we can see the whole thing. Basically what we're going to do is we're going to make a plot, and we're going to plot the concentrations. I've actually taken the concentrations and multiplied them by 1,000 just to get rid of some of these leading zeros, which are a bit of a pain. You can do this, but if you do this, you have to remember to divide your answer that we're going to look at in a second by 1,000 as well. I'll show you how to do that. It just makes the graph look a little nicer because your x-axis doesn't have a whole bunch of zeros in front of every single number here, which can be a little distracting. However, if you want to, you can just plot the original numbers as well. Let me show you what that looks like. This is the original number. If we just drag it over, you can see it gives you the exact same thing, just different by a factor of 10 to the third. And it just puts a bunch of these zeros in there, which are kind of not the most attractive looking thing. So this is usually a standard technique for making your graph look nicer. You use some power of 10 as opposed to the standard unit. Anyway, so we get our equation. So basically this is a calibration curve. So what it says is that these are the known concentrations of our ion. That's what's on the x-axis here. And these are the known absorbance values. So what we've done is we started with some known concentrations. We made these solutions so we know what the concentrations are, and we measured them so now we know what the absorbance values are. And now we have this nice line, and the line has an equation, and the line tells us, and to remember to add the equation, you click on your data and hit add trend line, and when you hit add trend line, you have the option of displaying an equation on this chart, displaying the r squared value in the chart, all that kind of good stuff. So we'll can't close that for now, but that's basically where this comes from. And so you need to make one of these calibration curves, and then you will get an equation like this, and this equation is actually what you use for part B. So for part A, what we did was we started with known concentrations and measured absorbances and made this curve. For part B, we're starting with unknown concentrations, but we measured their absorbance, and what we do is say that we have a value and it's 0.25, and so we come over here to 0.25, we go across to the line, see where 0.25 is, and come down, and that tells us what the concentration of our unknown was. But that's exactly what this equation does. This equation says whatever's on this axis is equal to 2.2575x minus 0.018. So if we solve this equation for x instead of y, right now it's y in terms of x, but if we kind of invert that, if we solve this for x instead of y, so it would be y plus 0.018 divided by 2.2575 equals x. And what we can then do is plug in the value of an absorbance for the y and solve for the x, and it will tell us what the concentration is. So this is how a calibration curve works. You use known samples, generate the curve, and then you work backwards with unknown samples. You measure your unknown samples, use the equation, but going the other direction to figure out what your unknown x's are. And so that's what we've done for these 4 different data points here. So here I've got 4 different data points. Again, these are the absorbances. This was the blank. So we need to take the absorbance minus the blank, and that gives us this number here. These are the corrected absorbances. Here is the iron 3 and the thiocyanate. Notice it's very different this time. We use equal molar amounts, 0.002 and 0.002 for our starting solutions. And then we didn't mix them equally, but very close, 10 and 2, 10 and 4, 10 and 6, 10 and 8. So these are very much closer in concentration. This top one was flooded with iron 3, and it caused the reaction to shift entirely to products. This one, there is no flooding. There's nothing in huge amounts of excess, so we don't know what the product concentration is, and that's how we can use it to calculate the equilibrium constant. So what I've done is I've set up 4 different ice boxes. Here's an ice box, here's an ice box, here's an ice box, here's an ice box. This is for blank, well, see, we named it solution 5. This one is for solution 6. This one was for solution 7, and this one was for solution 8. Okay, and then I started with what my known concentrations were. Well, what my known concentrations were from these numbers here, 0.002, and again we're going to use N1V1 equals N2V2. These actually did go to 20 milliliter solutions if you look in your handout for this lab. So you would have the initial concentration here times the initial volume divided by the new volume, which was 20 milliliters, and the same thing for the other one. So here are the starting concentrations for the iron 3 and the thiocyanate for solution 5, the iron 3 and the thiocyanate for solution 6, for solution 7, and for solution 8. The starting concentration for the complex ion is 0. We didn't add any of that, so it's 0. Now we want to figure out what the change is. Now notice I've got this change written in here, but you'll see in a second that I did not just write these numbers in. These numbers are actually calculated. Let's see how they're calculated. The way they're calculated is because I have these absorbances. So notice what this absorbance is that says for solution 5, we measured the absorbance to be, after correction, 0.151. Okay, so that's our Y value. That's the Y that's on here. So we take this 0.151 and we plug it into Y in this equation and solve for the equation. And that tells us the equilibrium concentration of the thiocyanate ion for solution 5. That's this number here. So if I look at this number here, let's look and see what's in our formula bar. I have the original value minus the blank. So what's red here is the blank. So that's this 0.151. I could have just as easily just used this number here. Would have worked the same way. So that's the 0.151, and then here's the rest of that equation. I subtract 0.0018, there it is, and I divide by 2,257.5. Notice over here this number was 2.2575, so why did I divide by 2,257? This is making up for the fact that up here I multiplied this number by 1,000. So here I'm dividing this answer by 1,000, which is the same thing as multiplying the denominator by 1,000. If you don't do this little trick of trying to make your graph look nicer by multiplying by 1,000, if you just use, I'll do it one more time, click here, and just use the original starting concentrations, notice it's 2,257, which is exactly what I actually have plugged in to my equation here. So that's actually the correct number to use. So this is using the calibration curve, and it gives me this number. Well, if I started with 0 and I end up with this amount, then that must mean the change was that amount. 0 plus some number gives me that number. So this number is the change. And this was the product, so my reactance, since these stoichiometric coefficients were all 1, is just minus that number. So all I've done is taken minus this number. Minus equals minus D18, that's the number in this cell. So minus that number for both of these points here. And then I start with the initial, add to it what the change was. The initial is 0.001. The change was minus 5.891 times 10 to the minus 5. And this gives me my equilibrium concentration. So now I have this equilibrium concentration of the thiocyanate ion comes from the calibration curve. These two come from this change. So taking whatever we got from the calibration curve and subtracting it from our starting concentrations. So here we have 3 concentrations at equilibrium, and the equilibrium constant is this concentration divided by this concentration times this concentration. Okay, so this is our product. These two are our reactants. Products divided by reactants, everything has a stoichiometric coefficient of 1, so you don't have to worry about raising to any powers, and that's where I calculated my equilibrium constant. So if you look here, I have product, D18, divided by reactant times reactant, and that's my equilibrium constant, 443.72. Now, there's a lot of error in these experiments. This is not the best instrumentation, so we did it 4 times, and I've got 4 relatively different equilibrium constants. But notice that they're not really that far different. Even if you look in your textbooks, the equilibrium constants that we are given to you in your textbooks usually only have 2 significant figures in them. They're usually something like 1.8 times 10 to the minus 8, or 4.7 times 10 to the minus 5, or some number like that. So when we take these and average them, we only really have 1 digit of significance. If we look at the average, 509, and the standard deviation, 250, well, this is really 500 plus or minus 200, 500 plus or minus 250, something like that. Which is not great, certainly is not great, but it's not terrible for the kind of cheap instrumentation that we had and the quickness and ease with which we were able to set this experiment up and perform it. So this is basically what I want you to do. I want you to work through this, build some ice tables like this on your own, and make a calibration curve like this. And I want you to, I effectively just want you to email me your data file. You don't need to print this and bring it to me. I want you to email it to me so that I can look at your numbers and make sure that you're setting things up. And I do want you to show these as calculations, not copying the numbers that I have here in place. I want you to show I want you to show these numbers and actually do the calculations so that you can learn to use Excel to perform these kinds of calculations for yourself. If you have any questions, I'll be glad to help you. And this will be due at some point at the end of the week, probably Friday. Even if you're in the Thursday lab, I'll take it on Friday. So if you have any questions, please ask me at some point during this week, and I will help you set this up. And then again, you can just email it to me, and that will be your last piece of lab work for the semester. I'll have some more to talk about tomorrow as far as some of the other stuff that we're going to do in lab, but this is the biggest part of it. So, okay, thank you, and I'll see you guys in the morning.